It's actually really hot in here.
Okay, today in class we are doing a circuit, which is a bunch of problems that kind of have the answers to them. So we're just going to get lots of practice. Okay, so here we have the graph, right? There's some graph we're calling h is the interval from 1 to t of this function. And we're going to use that some points in here. But we're just going to start here in the first box and find this, right? So it says, let me make it larger so we can see it. Just zoom into this one and get rid of that. Come here and get you out of the way. Okay, so capital F is the integral from 0 to x of 5 dt. We want to find f of 3. Okay, so they're asking us to replace x with 3 and then figure it out. Okay, so we put 3 here, f of 3. We now have the integral from 0 to 3 of 5 dt. Okay, so we are going to try and find the antiderivative of 5 dt. So the antiderivative, right? We want to take an antiderivative of 5. If 5 is a constant, then the antiderivative is 5 times a variable to the first power divided by 1. Because that's how we do a polynomial. But we don't ever write to the first power or dividing by 1. And we're going to evaluate this at 3. And we're going to evaluate it at 0. And 15 is your answer. So let's find 15 on our other sheets. Here it is. 15 is right there. So we're going to put number 2 right there for 15. Sorry, I'm discombobulating everything. So g is the function from x to 2 of t dt, the single variable t. So once again, we want to find g of 4. So we're going to have to anti-differentiate t and evaluate it from 4 to 2. So g of 4 is the integral of 4 to 2 of t dt. Okay? So the question becomes, what is the antiderivative of t? And that is t to the second power divided by 2, or if you're so inclined, 1/2 of t squared. And we're going to evaluate that at 2 and subtract it when we evaluate it at 4. Okay, so when you evaluate it at 2 and subtract the evaluation at 4, we get -6, which is over here. Okay, oh, so look, we're trying to find f prime. Okay, so that should let you think about the fundamental theorem part 2. Right, so if you remember that, if you don't remember that, here, let me write it down for you. I just got to change my color so you can see it. If f is the integral from 0 or from a to some function, right? So we have a variable of integration of some function here. Then f prime, right, the derivative of our integral is found by replacing your variable in your function with that limit of integration and then multiplying it by the derivative of that limit of integration right there. Okay, this is only good when we have a variable as our upper limit of integration. So f prime g of t times g prime of t. That's how we take the derivative of an integral. So we're going to do that here. We're going to take our x and we're going to plug it into here, and then we're going to multiply it. So f prime of x, I understand yellow is not a very good color for this. F prime of x is equal to the square root of 1 plus x times the derivative of x, which is 1. Okay, so you put x into your function, and then you multiply by its derivative. In this case, the derivative of x is 1.
Is it the chain rule, right?
That is indeed the chain rule. So now when we evaluate it at 15, we replace x with 15, and that gives us your answer. Okay, so that one will lead us straight up here to this problem. Okay, and once again we're asked to find the derivative of our integral. So we're going to take your variable of integration here and replace theta, right? And then you're going to multiply it at the end by x prime, which is once again 1. So g prime is the cosine of x plus pi over 2 times 1, the derivative of x. And all we need to do is replace x with negative pi over 2 and know your trig. So negative pi over 2 plus pi over 2 is, oh, I don't know, 0. So from your unit circle, the cosine of 0 is that's always fun. 1. Okay, that takes us over to here. Wait, maybe I should do it this way. That takes us over to here. Okay, to this crazy looking problem. Okay, but it's not bad. So once again, we're trying to find a derivative of an integral. Okay, derivative of an integral. So we're going to put our variable into both of these, and you're going to multiply it by 1. Okay, so when we take the derivative of an integral, we no longer have an integral. It is 2t over pi times e raised to the cosine of t power, okay, times 1. So now we're going to do our substitution. We're going to replace t with 3 pi over 2. Okay? So f prime of 3 pi over 2 equals 2 times 3 pi over 2 times e to the cosine of 3 pi over 2. So let's do some simplifying. I have 2 times 3 pi over 2, so the 2's divide out, right? 2 divided by 2 is 1. And then I'm left with the 3 pi over pi, and the pi's cancel each other out, so I'm just left with the 3. Now the cosine at 3 pi over 2, that's at the bottom of my unit circle, where I have the coordinate 0, 1. And since cosine is the x-coordinate, right, this is 0. The cosine at 3 pi over 2 is 0. And e raised to the 0 power is just 1. So my final answer is just 3. Okay, and that takes us, where does that take us? Back over here to this one. Okay, so it tells us we have some position function defined by this crazy. So we have s of 0. This is its initial position, right? Its y value when time is 0, plus this integral of 8 over pi plus secant squared beta d beta. So once again, we need to plug in pi over 4 into our t value, I guess, is what we're trying to find, s of t, and do some integrating. Okay, so let's do this one piece at a time. Let's handle this part. Okay, so part of our properties of integration is if we have the integral of a sum, I can break that apart into the sum of my integrals. So the sum of 8 over pi d beta plus the integral of secant squared beta d beta from 0 to t. Okay, that's one of my properties of integrals. Since I have a sum inside of my parentheses, I can split that into the integral of that sum, or the sum of those integrals. Okay, so let's evaluate, right? We're going to evaluate each of these separately. So this one is, what's the antiderivative of 8 over pi? I believe that's 8 over pi times our variable, which I guess is beta, but we'll make it t. So 8 over pi t, because we're going to replace that with pi over 4 anyway. We're evaluating this at 0 and at pi over 4. Plus, what is the antiderivative of secant squared? The antiderivative of secant squared is tan. And we're going to evaluate that from 0 to pi over 4. Okay, so we're splitting this plus into the sum of two separate integrals, because maybe it makes it easier, maybe your brain can see it better, maybe it doesn't. Maybe you're amazing and you can just integrate it just fine. And it works either way. Okay, so this becomes 8 over pi times pi over 4 when we plug this in, plus 0, right? 0 minus 0, plus the tangent of pi over 4. So if we think about your unit circle at pi over 4, that's root 2 over 2 divided by root 2 over 2. The tangent is 1 minus the tan of 0, right? Once again, tan is y over x, so 0 over 1 is 0. Okay, so that is all of this part right here is now this right here. Okay, plus we have to add our initial position of negative 6. Okay, because s is the initial position plus my integral. So let's see what I can do here. I have negative 6 plus 8 over pi times pi over 4 is just 2 plus 1, because all these zeros are gone. Negative 6 plus 2 plus 1 is negative 3. Okay, and that takes us up here. Oh, so now we're trying to find w double prime. Okay, this is the second derivative. Okay, so if that means we have to find the first derivative first. So let's do w prime using the second part of the fundamental theorem. We're going to replace x with our variable of integration, so t minus 1, times 1, because you have to multiply it by the derivative of that variable of integration also. So most of the time today, that's been just a derivative of 1. Okay, it won't always be that way, which is why I'm doing it every single time, so that you know to multiply by the derivative of that variable of integration. So if this is our w prime, then what is our second derivative? Take the derivative of natural log t minus 1. And then derivative of a natural log is 1 over t minus 1 times the derivative of t minus 1, which is just 1 also. Okay? So the derivative of a natural log is 1 over the parentheses, whatever that x value is, times the derivative of your x value. And now that we've calculated or written the second derivative, we can plug in 5/2. So 1 minus 1 over 5/2 minus 1. Okay, we get that, which takes us all the way over here. So remember, what does this symbol mean? It means the derivative. So this is another way of writing f prime, right? We're trying to find f prime of x. We're trying to take the derivative of an integral. So you're going to take your limit of integration and replace it into your formula, right? So we're going to call this f prime equals 2 over 1 plus tan squared times the derivative of tan, right? We'll always have to multiply it by the derivative. And the derivative of tan is secant squared. I guess our variable is t. Okay, so when we're taking the derivative of an integral, you no longer get an integral, you get a straight up equation. Okay, so now we're going to replace t with negative pi over 4. So this is what happens when you plug everything in. So now let's turn on our trigonometry brains and figure all this stuff out. Okay, so what is the tangent at negative pi over 4? Okay, so that's in the fourth quadrant, is negative 1 in the fourth quadrant. So the tan of negative pi over 4 is negative 1. Okay? And the secant at negative pi over 4 is the reciprocal of the x value. So the x is root 2 over 2, so the secant at negative pi over 4 is root 2. Okay, these all come from your unit circle, but hopefully you know a little bit better than you think you do, which is probably not true. Okay, so let's keep evaluating. We have negative 1 squared is positive 1, so 1 plus 1 is 2. 2 divided by 2 is 1.
Times 2.
And root 2 squared is just
2.
2. So 1 times 2 is 2. Okay, so yes, the algebra might be a little sloppy, but we take it one term and one part at a time.
I got 0.
Okay, 2 takes us. Where does 2 take us? 2 takes us over here. The next questions are about h. So now we're going to go to our graph. We want to evaluate h of 1. So let me slide over here.
The answer is 0.
H of 1. So I'm going to do it right here in front of us. I guess in front of me. So h of 1 is the integral from 1 to 1 of our graph. Okay, so if your lower limits and your upper limits are the same, then we don't have any width to our rectangle, right? It has a width of 0, so that means the area under the curve is going to be 0.
Wow.
So h of 1 equals 0. And 0 takes us over here. H prime at 3. So remember h prime we find by replacing your variable with your limit. So we're going to put t into here. Okay? So basically what we're saying is h prime is equal to f of t, right? Of course times 1, because that's the derivative of t. But the slope of your, right, your rate of change of your area is equal to the y value from your graph. Okay? So if we're trying to find h prime at 3, we're looking for the y value when x is 3, and that y value happens to be? Negative 2. Okay?
Negative 2 times 1.
So let's slide on over here. H prime at 3 is negative 2. The y value there. All right, let's see. Where does that take us? Right here. H double prime. So remember from 1 second ago, h prime at t is equal to f of t. We calculated that. So let's take the derivative of f, and that gives us f prime. Okay? So it takes some understanding. What is f prime conceptually? The slope of the line at any value t. Okay? So if we're trying to find h double prime at 1, we come up to where x is 1. Where is x1? And we find the slope of this line. So what is the slope of the line at 1? Looks like that slope is negative 1.
Because you do y1, y2 minus y1.
And this takes us to our last question over here, h of negative 2. So we're going to evaluate the limit from 1 to negative 2 of our function. Okay, so let's come over here and see what that area under the curve looks like. Okay, so we're evaluating it from negative 2 to positive 1. So here is our shape. Okay, this is a bit of geometry. We have a rectangle, so what's the area of my rectangle? 2 because it's literally 1 unit high and 2 units wide. And this is a triangle with a height of 1 and a base of 1. So 1/2 of 1 times 1 is 1/2. So the area from -2 to 1 is 2.5. Okay? But that's not what we want. We want the area from 1 to -2, which is the negative of the area that we found from -2 to 1.
Wait. Oh, it's just the opposite?
If your lower limit is less than your upper limit, the area is the negative of what you calculate. So because our area from -2 to 1 was 2.5, when you switch your limits of integration, your area becomes negative. So -2.5 is our answer, and that completes our circuit.
I've been trying to get everybody to clap all day.
They always love it when that happens. Hopefully that helps, and you're better at taking limits of integration as well as derivative of limits. Have a great day.